Hi everyone, today me and my teammates will be presenting the application of linear systems in engineering and science field. Today's presentation will be break into three parts, which is the application in computer science, electrical engineering, and also aerospace engineering. That's the overview for it. I will be the first speaker today to guide you through the first section, while my group mates Lo Zhongyi and Lai Yongjie will be covering the second and third section respectively. Not wasting too much of time, let's proceed into our first topic today, the application of linear systems in computer science. In this case, to make things clear, we will more concentrate on some specific examples on how linear system related to computer science. For example, linear system is very helpful in computer vision. Firstly, we all know that linear algebra allows us to turn a linear system into a matrix where we can deal with a higher dimensional problems. And if you think carefully, this is exactly what we want in computer vision. Instead of dealing with the cartoon's animation, we would like to make use of the computer vision technologies to work for us in our three-dimensional real world. Hence, we came out with a bunch of codes like NumPy and TensorFlow in the coding language, which allow us to compute a matrix that help us to cope with the videos, static images of photos, and even live camera. And these are all the well-known technology where we use every day, like Instagram face filter, online banking face ID, and image processing. Maybe up to this point, it is still a bit vague for you, but let's dive into it more details, and I will show you the direct relation between linear algebra and computer vision. So I'll be using the example of face recognition technology to ease my explanation so you can have a better understanding on it. You might be asking why we choose to use linear system to manage our videos or photos rather than any other ways else. Well, the reason is very simple. Just imagine today you want to make a face recognition program, and definitely you need a tools that can detect a multiple dimensional image to ensure the accuracy of your program, and you want it to really recognize each different persons with their faces, right? So to make things simple, we can just encode all the faces detected by the system into a vector and stack them all together. Within this process, we might need different vectors to represent different landmarks on the person's face. For example, his eyes can be represented by a three-dimensional vector A, B, and C, while his nose can be represented by D, E, F, and vice versa. By stacking up all these landmarks vectors, obviously we will be getting a three-dimensional matrix in the end, where these matrices represented different persons' faces. And yeah, that's the intermediate steps that is missing and causes the confusions to most people on how linear system related to computer vision. The main process is just basically to break down the images or videos into a matrix that can be understood by a computer by making use of the vectors, and this is what we call image encoding. In this case, the objects detected by the system are humans' faces. So the landmark vectors for each person definitely will be different, and that's how the computer get to differentiate each person by their faces because of the matrix that is formed by different vectors. After these main steps, everything is just goes back to the normal comparison. For example, if we insert a picture of person A to let the computer encode it, and after that, we open up the live camera for the computer to detect the real face of a person A. And the computer can be asked whether the picture belongs to person A or not. Well, this is basically just compare two matrices and see whether they are row equivalent. Most of the time, we don't really get exactly the same matrices, but we can set a tolerance rate within a range normally should be 0.6, meaning that the matrices could be off by at most 0.6 value. Within this range, Both matrices are considered row equivalent. That's why our computer can tell exactly is that picture A and person A is the same person. This is how the linear system helps in a face recognition technology. Another good things about linear system written in matrix form is because of its flexibility. For example, if today we are willing to edit or process an image, obviously the computer cannot detect the image with raw eye like how we do. But what the computer can understand on the image is basically just the matrix formed by the image. Like we mentioned earlier on, the image is formed by several vectors represent different part of the image, or to make it short, we can just call it as the pixel value of the image. By simply changing this pixel value, we can change the brightness, color, shape, size, or many other things else of the image. And that is how normally the image processing works. Besides that, we can also do the transformation of matrix. Each transformation of matrix represent different condition of the image. For example, normally people taking picture by facing the camera directly. If someone who take picture of his or her side face, the matrix that represent his or her face will undergoes a certain transformation. So the computer can know whether the person is showing his or her face or side face in the image. Other than that, we can do some even powerful transformation like rotating the images upside down or even resizing it. So that's the good things about using a matrix to manage an image, because we can just customize or edit the image as what we wish. So that's all for my part. And now I would like to pass over the presentation to my group mates, Lo Zhongyi, to continue with his section. Thank you.
I'm going to talk about node voltage method, which can be applied in electrical electronic engineering. I will explain how the node voltage method leverages linear system to solve direct current circuits. This method is widely used in electrical engineering to analyze circuits and determine unknown voltage at different nodes. Let's start with this example of direct current circuit. This diagram shows three resistors R1 12 ohm, R2 4 ohm, and R3 6 ohm, along with a current source I3 ampere entering node 1 while node 2 connected to ground. First, it is important to understand what a node is. Nodes are connection points where components meet and their positions can be determined using nodal analysis. In this example, V1 is identified as node 1 and V2 zero voltage is designed as ground node. Next, here's where linear system comes in. The equation GV equals I can be obtained by substituting the formula G equals 1 over R by substituting G into Ohm's law formula, which is 1 over R V equals I. This equation represents the relationship where G is the conductance matrix built from resistor values. In this equation, V represents the vector of node voltage and I represent the vector of currents flowing into the nodes. Using dot product, the node voltage can be efficiently calculated as shown here, which the final answer V1 is equal to 7.2 voltage. We can prove this answer by using Kirchhoff current law KCL. It states that the sum of currents entering and leaving a node is 0. The current flow of the circuit from I1 split into two branches, I2 and I3. Both left and right side of the circuit have the same currents flowing in a clockwise direction before returning to the ground node. By substituting Ohm's law, I equals V1 minus V2 over R into KCL, we can get the answer that V1 equals to 7.2 voltage, which is same as previous answer. The node voltage method, which relies on linear system, has practical applications in various fields, such as power systems, circuit design, and signal processing. In power systems, it is used to analyze voltage level in electrical grids. In circuit design, it ensures the proper functioning of electronic devices. In signal processing, it provides insights into the behavior of more complex alternating current circuits. In conclusion, the node voltage method highlights how linear algebra simplifies the process of solving electrical circuits by converting complex relationships into manageable equations. This approach is not just theoretically, but is widely applied in practical electrical engineering scenarios.
So for my part, I'll be talking about the use of linear system in research civil aircraft model, which is basically a model for airplane flight. So what is RCAM? So RCAM is basically a document that covers models ranging from plant models, sensor models, actuator models, control designs, etc. But today I'll only cover the plane model. So basically, what the plane model from the RCAM does is that it will take a bunch of inputs. For example, the aileron, tail, or elevator, the rudder, throttle one, throttle two, take all these inputs, and then it will go through a bunch of algorithms, calculations, and then it will get this X bar, which basically is the output, or how the inputs directly impact the plane. So for example, the velocity for all three axes, x, y, z, and then the angular velocity. So there's also the three planes, and the bangular angle, pitch-angular angle, all these angles are okay. So like the rotation, and then example of use. Okay, so basically for this part, the outputs from just now, let's say we feed some example inputs and then we get like output, right? So the matrix of the output will come out to be something like this. So this x1 to x9 will come out to like this. But the problem with this is a bit hard to study because it's a bit complicated, it's a bit messy. So what we can do is that we write in matrix form, so the linear system convert into matrix form, and then we can find like, okay, let's say this all this zero, and then we compare with the variables and then see uh, like which part got affect each other or not lah. So this can help us simplify the calculation and analysis. So we know that the longitudinal variables are these. So x1 to 1358, and the lateral one is x2467. So we can try to separate this. So let's say we do a linear transformation, and then we can simplify that one. So yeah, see the lateral and longitudinal axis is like not affect each other. Okay, so we do like a linear transformation. No, the matrix transformation, and then we transform it into something like this. So now we can see that, okay, that this part doesn't affect this part, because okay, I'll explain it later. But basically, we separate this and we can group it into like two different matrices later. So this example, so what I mean is, let's say you got x1 to x4, and then we know that x1, x2 is for the x-axis, x3, x4 is for y-axis. So what this means, let's say for this matrix, since the back here is all zero, that means this two part in the top is actually only affect x-axis, because x3 and x4 is always zero. So actually the first two variable not affected by second two variable, and same goes to the below here. So x1, x2 is always zero here. So that means the y-axis will not affect the x-axis. So basically that's the idea. So you can separate the whole matrix into two different set of equations, basically. So then you can separate into horizontal and vertical. For that one, you can separate into uh, lateral and longitudinal. Yeah. So that's basically how one of the examples of how a linear system is applied in this RCAM model. Okay, this plain RCAM model. And then so for short conclusion, so linear systems are used in many fields. And then it can help us study the cause and effects of real situation mathematically. So we can have like a proper study instead of just assumptions and opinions. And then it can help simplify all these complicated calculations, and for machine learning it can help develop algorithms for this machine learning. Okay, so that's basically a short conclusion as to how linear system is used in different industries, different fields. Okay, so that's it from me. Thank you so much.